Hey everybody, we're here today to talk about an introduction to exponential functions. If you haven't already taken a look at the video on scale factor and percent change, go ahead and check that out before you go on. Percent change, remember, is the percent as a decimal that a value changes relative to another value, and the scale factor is a number that scales or multiplies a value relative to another value. In our first example, in the episode A Wrinkle in Time, Morty and Summer cause time to split in two, and then Rick causes time to split a second time. Now Schlimmy Pants shows up in order to fix things, and to do that he gives each of the characters a time stabilizing collar. Now time is split so much that at one point Rick says that the different versions of himself need to fix all 96 collars to get it back down to one reality. So the question is, how many times has time been split? So take a second, pause the video, and see if you can't figure that out. So hopefully you've had a chance to try that. Okay, I'm going to start by making a table. So we have the number of times that time is split and the number of collars. Okay. Now, initially, before time is split, there were 3 collars, right? That's what we know to begin with. Okay, that's our first reality here. So now take a second, see if you can't fill this table out. Okay. Now, after the first split, we now have 2 realities. So instead of 3, we now have 6 collars. Okay. Now, when it splits again, we now have 4 realities, and between those 4, we now have 4 times 3, 12 collars. So we can start to see a pattern. If we were to split that again, it would end up doubling again. So we see this pattern of doubling that's happening, okay, between our terms. Now, if we keep going with this pattern, we're going to notice that it's going to take 5 splits in order to get to the 96 Ricks, or the 96 collars that Rick is talking about. Okay, so take a second and pause the video and write down any observations. What do you notice and what do you wonder? Hopefully you've had a chance to check that out and have an answer for that. So maybe you've noticed that the scale factor is constant here, right? And that is definitely something there. And maybe you wonder if it's going to continue. And that's a good question. In this case, it definitely will. Example number 2, murky water. So we have 100 gallons of contaminant that has leaked into the school's water supply, and a company says they can remove 10% of the contaminant each day. When will the water be safe to drink? So in this one, we're talking about percent change, right? And this one's negative, so we're talking about decay. All right, so if we go ahead and make a table, we could have T be the number of days and maybe G be the number of gallons of contaminant. So take a second and fill your table out with the initial value. We're going to have 100 gallons to begin with. Now, if we're taking out 10%, 10% of 100 is 10. So we can take 10% out and we're left with 90 after that first day. Now 10% of 90 is 9, so we could take that out and we're left with 81 gallons after the second day. We can keep going, subtracting 8.1 gallons to get 72.9, and we can keep going, all right? Just forever and ever and ever. But it's a loaded question. When is it going to be safe to drink? I mean, it's probably not, right? It's contaminant, so it really doesn't matter how much is in there, okay? 1 gallon, half a gallon, we can keep going and figure that out. But there's a couple key things that we want to consider here, right? There's places like Flint, Michigan that are dealing with water contaminants, places like Puerto Rico where people can't get clean water, and even schools within our own district where students don't have access to clean water. So that's kind of the important thing to consider. Is this ever going to be clean? No, it's not, right? It's never going to be safe. So if we take a look at what's really going on here, this is a percent change, and that percent change is the same every day, right? We're taking out 10% every day. So in this case, our percent change is constant, all right? Now, for what we know is that there's this connection between percent change and scale factor. If we take a look at what our scale factor is, we've got 90 over 100. That's 0.9. Okay, 81 over 90, that's 0.9. 72.9 over 81, that's 0.9. And again, we shouldn't be surprised, because if we use what we know, we take the 100% and we subtract off the 10%, and we end up with 90%. Okay, and that's what our scale factor is telling us, is that if we take out 10%, what we have is 90% each time. And we could continue this pattern. You could keep multiplying by 0.9. For instance, see how long it takes you to get below 1 gallon. Okay, you'd be surprised. So our big result in both of these cases is that the percent change and the scale factor were constant. And that's what makes an exponential function, right? We have a scale factor, this number that multiplies between the values, okay, the output values, over the same interval of the input values, okay? So for our practice problem, we have a magical box that produces gummy bears at an exponential rate. So we already know it's exponential, but let's go ahead and verify it. Okay, before we answer the question of how many gummy bears there will be after 2 weeks, let's go ahead and verify that this is in fact an exponential function. So we have 12 over 3. We're going to find the ratio of the terms. 12 over 4, my bad. And that gives us 3. And then 36 over 12, that also gives us 3. 108 over 36 gives us 3. And the last one, 324 over 108, gives us 3. So we can see, yes, we do have a constant scale factor. Right? If we wanted to figure out what is the percent change, well, we've added 8 gummy bears this time, and that's 200%, right? 4 times 2 is 8, so that's 200%, and that vibes. 100% plus 200% gives us 300% that we would get for our scale factor. Okay. So then now we want to answer our question of how many there will be after 2 weeks. So you keep going, we could just keep multiplying, but we could also just take a look at the pattern. We started with 4, and then we're going to multiply by 3 over and over and over, okay? And we're going to do this for 7 weeks, okay? Right? And so since we are multiplying 3 7 times, we can just rewrite this expression as 4 times 3 to the 7th. And when we plug that into our calculator, we end up with 8,748 gummy bears. Okay, it's quite a bit. Okay. So hopefully that helps you get working on the practice for these sections. Good luck, and come to Zoom hours with questions.